I will talk about testing ultra-high energy cosmic ray origin hypothesis using deep learning. This topic was already partially covered by in talk by Jonas. So basically, just a second. The problem is following: we want to reject some null hypothesis. For example, isotropic flux. If we believe that some alternative hypothesis is true, and as an observations, we use the arrival directions of cosmic rays with energies above some threshold, say 57 eV. And the problem is hard to solve for ultra-high energy cosmic rays because of their deflections in magnetic field, especially magnetic field of our galaxy. You see on this map that the deflection angles are quite high, and for here by star we show the position of the original source CNA, and the position of simulated events is shown by color circles. So this is not a really spot like it would be in case of, for example, gamma ray source. So methods like counting number of events around this source position don't work very well, and we need to invent something more clever. And basically my talk is about the test statistic based on machine learning methods. Okay, for the null hypothesis, we will use the isotropic flux, and for the alternative hypothesis, we will use some quite promising model which explain both spectrum and composition of ultra-high energy cosmic rays as measured by Pierre Roger. And this particular scenario assumes that ultra-high energy cosmic rays are produced in a subclass of active galactic nuclei. The energy spectrum, the original energy spectrum is power law with rigidity-dependent cutoff. And the cosmic rays first propagate through the zone dominated by photohadronic interactions, and then through zone dominated by the hadronic interactions with gas. After that, they propagate through extragalactic space, and finally they reach the Earth, but on their way to the Earth, they are also deflected by galactic magnetic fields. So this model is quite nice, since we like it because it allows to explain both spectrum and also Earth shower maximal depth measurements. And in addition, it also allows, as you can see here on the left plot, it also predicts secondary flux of neutrinos, which is quite close to what has been observed by IceCube experiment. And one of the consequences of this model is that there should be source within roughly 20 megaparsecs. So this is good alternative scenario, and we will try to derive the optimal test statistic to test to construct a test to reject the null hypothesis. Okay, how we reject the hypothesis? We need to select a threshold. Let's say we want the false negative probability to be 0.05, and this gives us the threshold for the test statistic. And as you can see on the figure to the left, we expect the test statistics distribution on built on zero hypothesis and alternative hypothesis. Those distributions are quite different. So if they are different, we can, when we choose threshold for false, based on false negative rate, we get the false negative value small enough. We hope to get it small enough. And this false negative rate value is given by this integral. And so we will be interested in the minimal fraction of the events from the closest source, which will allow us to get the false positive rate less than 0.01 if we fixed false negative rate to be 0.05. So this is our criteria. So with these conditions, we will try to find the minimal nearest source, minimal fraction of events from the nearest source. How we choose test statistic? Well, the very common way in this situation would be to use angular power spectrum. And this method is used in many works, for example, by IceCube and Oleg collaborations. And also in our previous work, we tried to use also angular power spectrum coefficient-based test statistic. And there are also other methods which may use, for example, the function of the expected arrival direction density maps, like it is done in telescope array correlation with large-scale structure analysis. And in this talk, I will discuss the method, which is based on convolutional neural networks. So basic idea here is to build a classifier which would discriminate the maps which were generated assuming isotropic distribution and maps generated assuming some alternative hypothesis is valid. And the first step in this procedure is, of course, map calculation. And the calculation is done in the following way. We emit a number of events, like from 100 to 500. And we assume that, for simplicity, that deflection angles in the extragalactic magnetic field are small enough. And we only take into account the deflection angles in the galaxy. But before that, we also have to account for interaction of cosmic rays in an extragalactic space. This is done by using public numerical code. And finally, we calculate the arrival direction density maps. And the example of such map is shown on the figure in the bottom of the slide. You can see here that this map was constructed for 500 events, 9% of which are coming from Cine. Now, if we use the angular power spectrum-based test statistic, we obtain the following numbers for the minimal from source event fraction in percents. Well, to interpret those numbers, well, we have to compare them with what we expect. And to do this, we can just simulate what we would see if there were a population of identical sources with certain concentration. So in the table on top of the slide, I show the fraction in percent of the flux for the nearest source and for the second closest source, depending on the concentration of sources. You see that this kind of method is sensible to the concentrations of densities of sources close to or below 3 × 10⁻⁵ megaparsec per cube. Now, can we do better? Well, let's try a machine learning-based study. So the idea, as I already told, is to construct a classifier which will discriminate samples generated in null and alternative hypotheses. The simplest possible classifier is just a perceptron, which takes as input angular power spectrum coefficients. And if we train such classifier, we don't get any improvement in terms of minimal detectable fraction. We get roughly the same numbers. However, in this case, we can interpret the weights of the classifier. If we plot the weights, we see that the maximal weights are for L equal between 3 and 5. So this is a very nice example when the output of the neural network training can be easily interpreted. However, we want to get more powerful models, more powerful discrimination. And for this reason, we want to use convolutional neural networks to capture patterns on the maps of arrival directions. And there are several implementations of the convolutional neural networks available now. And we were using just one implementation which appeared to be the most convenient for us. This implementation is based on Helpix grid. It is not very, I would say, very precise procedure, very self-consistent procedure, but it is accurate enough for our purposes, as we will see. So the convolutions are defined by the kernel of size 9. And so we, in our model, we have a sequence of convolutions. The initial image size is Helpix grid with n side equal 32 and just one channel. And after that, we produce 32 maps with downsampling the image and then repeat the procedure until we reach n side equal 1, after which we flatten the vector, the image to vector, and send it to dense layer. So this is the architecture. For training, we use roughly 100,000 samples generated in mixture model, where number of from source events distributed uniformly in log eta, and 100 samples generated from isotropic model. And here is what we get. On the table on top of the slide, you can compare figures obtained with convolutional neural network with previous method based on angular power spectrum coefficients. And you can see that in terms of the fraction from source events, we get improvement by factor of 2, between 2 and 3. And in terms of required number of events to be sensitive to the fixed fraction, the improvement is roughly factor of 4. So this is great improvement. And on the bottom of figure, I show the dependence of true negative rate on the parameter eta. And you see that with convolutional neural network based test statistic, we always outperform the angular power spectrum based test statistic, and also hotspot based test statistic, which was mentioned in the beginning. Okay, so we are happy, but let's remember that there might be some model dependence. And the most model dependent part of the procedure is the galactic magnetic field model. You can see here that the deflections of the 100 EeV iron nuclei, their dependence on the direction is maybe quite different for different magnetic field models. So unfortunately, this could strongly affect the performance of our procedure. And we need to, at least we need to investigate this. So what we have done, we have trained our classifier using a baseline magnetic field model, for which we assumed Jason Farrar 2012 model. And we also constructed maps obtained using different magnetic field models and tried to apply the test statistics to the maps generated for different galactic magnetic field model. And obviously we have seen that there is some overfitting. The classifier learns to give predictions which are particular for the specific magnetic field model. And to avoid this behavior, we decided to use a kind of early stop technique. That is, while training, we were still training our classifier using baseline magnetic field model, but while training, we were monitoring the performance of the test statistic on alternative magnetic field model. And when the test statistic performance stopped to grow, we stopped training. So that was kind of early stop technique. And with this kind of technique, we achieved quite a good performance for the test statistic, even in case of somewhat different magnetic field models. However, there are cases when the performance drops dramatically. Especially this is the case for the source M87 and the magnetic field model, which is marked here as TF17. So there are some combinations which don't work well. And to deepen to this reason, to the reason of this discrepancy, I have shown here the maps of arrival directions calculated for M87 source. And you can see here that if we assume this particular magnetic field model, the arrival direction map is quite different from the arrival direction maps which were obtained for other magnetic field models. So this is more or less expected result. And I should note that for the rest of sources and the rest of models, we have much better agreement. Now, next thing we want to investigate is model dependence, namely mass composition dependence. Although the scenario which we consider fits the mass composition observed by Pierre Roger, the mass composition itself has quite big uncertainty, and also if we remember that there is another experiment, the telescope array, which has also its own composition measurements, and their composition results are quite different. That's that leads us to the idea that we need to figure out what is the mass composition dependence. And here we try to shift the mass composition, the original model mass composition, towards 2 times more light, or 2 times more heavier. And as a separate exercise, we just replace the composition by the composition measured by telescope array 10-year data. And here is the result. You can see here that if we apply the same classifier based on the original model to the maps generated with shifted mass composition, we get roughly similar results, again, except the case of M87 for the special magnetic field model. Okay, now also, since in real life we expect that there will be considerable contribution from not only from the closest source but also from the second closest. You can see that the contribution from the second closest source could be factor of 3 below the contribution of the closest source. And in this exercise, we added admixture to the map generated from CNA. We added admixture of 1/3 of events from M87. And we have applied, again, in this case, we have applied the classifier trained on the maps generated with CNA only source. And again, we have quite good performance, except for magnetic field, for very different magnetic field model. And so far we trained for every source, we trained a separate neural network as classifier. And one could train single classifier for a number of sources. And we did this exercise and have seen that although the performance drops slightly, still we are in good shape. We get much better results than one could get using the angular power spectrum-based test statistics. However, if we test this universal classifier on sources which were not involved for training, then we get numbers which are worse, and those numbers are similar to numbers which we get with angular power spectrum-based test statistics. Okay, so now to apply this analysis to real experiment, we need to take into account a few problems. First of all, the exposure can be non-uniform. The angular resolution is also not infinite, and energy resolution is also some finite resolution. So to take into account these limitations, we can do the following things. First, non-uniform exposure is very easy to
sorry to interrupt. This is the last talk, but we already 5 minutes out of the schedule.
Okay, I have just 2 slides more.
Okay.
The exposure can be taken into account very, very easily by weighting. The finite angular resolution can be taken into account by map smearing or by limiting the resolution of the HelpX grid. And the most difficult thing to take into account is finite energy resolution. And here we have to take into account that lower energy events contribute to maps and to deflection to the maps of events, and since they are deflected to much larger angles, their maps are smeared, and this is real trouble. but we found a way to compensate for this compensate this problem by introducing binning. In addition to smearing in energy, we introduced binning in energy. So we were able to take into account the fact that the deflection patterns are different for different energy bins. So when we're using binned energy maps, now the model is slightly different. It has many maps. It takes many maps as input. And for this kind of model, we get roughly the same numbers, slightly worse numbers than we had before. So my conclusions is that we can apply this analysis to real experimental data. And the advantage of this analysis is that it's kind of optimal because we trained to discriminate, we trained the classifier to discriminate two hypotheses. It's easier to apply to non-uniform exposure. However, it is not very easy to interpret since it's neural network. Thank you.
Thank you very much. Are there any questions? If there are no questions, I have a question. Actually, Mikhail Kuznetsov.
Okay, Alexander, go ahead, and I will ask after you.
Okay, my question is, if I understood correctly, the primary aim of using those convolutional networks is to determine the weight of different signals, the best weight to sum up different signals to get this optimal criterion, optimal statistic for your data.
No, this is only the case for this toy example of neural network when we trained our classifier, simple classifier, to discriminate the two hypotheses, and we can look into the weights which it has trained, and by looking at those weights, we can see which particular coefficients are the most important, on which angular scales, yes. Based on which angular scales we give the answer. But this is only a toy example which shows that still we can use neural networks and interpret the results. This is very funny.
Okay.
However,
the reason I'm asking, I understand then there is a question how it is better than the likelihood analysis, but to save time, I just want to point you in direction that it is possible if you know your loss function, your likelihood function, or however you call it, then there is a way to analytically define optimal weighting. And then you can do a classical analysis without neural networks. You just can define which signals contribute the most to your discrimination between theories. The work was done by late Fyodor Tkachov, and for example, one of my students currently working. It's based on the Fisher information. Okay, then there is a question from Mikhail, and then there is another question.
Oh, okay, Oleg, thanks for interesting talk. I would like to ask the naive question. So, did you try, or is it possible to take on input of the neural net not the continuous model map, but rather a set of events, cosmic ray events generated assuming this model map, and train a network on this sample? And in potential, this could be much faster, and also you could avoid the problems you discussed in your last part of your talk with the energy resolution, angular resolution, and so on.
I wouldn't say that this would allow to avoid problems with angular resolution, because in any case, we need to make smearing.
Yeah, you need to make smearing, but you make it on a stage of set generation.
That's right. And for the you're talking, perhaps you're talking about the method which was introduced by Jonas today's talk.
Maybe, yeah, maybe I'm not grasp the details of Jonas' talk.
I haven't seen numbers, final numbers in his talk, so I cannot compare. But it would be interesting to compare the performance of those two methods.
Okay, maybe I need to look for literature, in particular for you.
There is a recording, you can listen to it again, and there is a second question actually from Jonas.
Okay.
Yeah, okay. Are you really sure? This the angular resolution is, do you think that it's really such a big thing? So angular resolution is something like 1 degree, right? But like composition dependency or something like this should be way larger uncertainty, right?
That's right. Yeah, the angular resolution is not a very big problem. The uncertainty due to the mass composition and due to our poor knowledge of the galactic magnetic field is much larger. Yeah, that's right.
So my question was that you checked this on a TI composition, the scenario, and estimated the numbers, but like this is an optimistic case because like the Auger composition is heavier. So did you already also check that and have a look at the number if you use the Auger composition, which is just heavier, especially at high energies?
That's okay. Here is the slide. So the model which we were, this study was based on, have fitted the Auger composition. And on this particular slide, we tried to use lighter composition and heavier composition. And here, by the red curve, I show the figure obtained, the numbers obtained for telescope array composition. And so you can see here that the test statistics is always, can also be applied. And the test statistics was based on the samples built with original model, which assumes Auger composition. So my conclusion is that this the classifier which we got and the test statistic based on this classifier can work, is quite universal. Yeah. Still, there are some cases when it doesn't work. For example, very different magnetic field, but it is not very strong composition dependent.
Okay, I see the point, but still, I think the composition scenario, so at the highest energies, so like 57% protons is not really realistic, right? If you check the Auger measurements, but still, you're right when you're saying that like the red curve is really close to the yellow and the blue one, and only the green one is just much further away. But still, it would be interesting to see that, because it's energy dependent, right? So at high energies, like it looks like there's much less.
Well, at highest energies, we have much less events. This is also another. This could be a reason that it's not very sensitive to the highest energies.
You're right. Yeah, maybe this. Yeah, one has to consider this also. Yeah. Thanks.
Thank everyone, and I think it's time to end today's session. We're a bit out of time, but it was really interesting, and I hope tomorrow's session will be interesting as well.